In this video, I'm going to work through the combined gas law sample problems in the PowerPoint slides. Okay, so remember the combined gas law is used now when we have more than just one variable being changed, okay, for our gas. So the first question appears on slide number 20. And that question reads, a sample of a gas has a volume of 4.28 liters at a temperature of 10.2 degrees Celsius and a pressure of 42.2 millimeters of mercury. What would be the volume of this same gas sample at a pressure of 4.56 kilopascals and a temperature of 21.3 degrees Celsius? Okay, there is a lot going on in this problem. Okay, these are a little bit busier, but let's break it down. So recall the combined gas law. Initial pressure times volume, right there we see that looks kind of like Boyle's law, divided by moles of gas, Avogadro's law going on there, and your initial temperature. Okay, here we've got Guy-Lussac's law and Charles's law. Okay, so everything's been kind of smooshed into one. Set that equal to your final conditions. But you'll recall, okay, in a lot of these problems, the amount of the gas is not changing. Okay, so your moles of gas are the same on both sides of your equation. You're dividing by the same factor in each denominator. Okay, so oftentimes we can kind of ignore the moles of gas and really just consider pressure, volume, and temperature for this equation. Okay, so in this problem, initially we've got 4.28 liters of gas. Okay, at a temperature of 10.2 degrees Celsius. Okay, you know you need to convert to Kelvin. You'll notice I'm kind of dropping that 0.2 degrees Celsius. Okay, I like to keep these all at 3 sig figs. I'll try and be really aware of sig figs on tests and quizzes and stuff like that. Our initial pressure is 42.2 millimeters of mercury. Okay, we already know we need to convert that to atmospheres. There's 1 atm and 760 millimeters of mercury. Okay, so our initial pressure is 0.0555 atmospheres. Okay, and then the question says, what would the new volume be? Okay, so we know we're solving for V2. If the pressure is changed to 4.56 kilopascals, do a quick conversion, right? 1 atm is equivalent to 101.325 kilopascals. Okay, so our final pressure is 0.0450 atmospheres. Okay, and our final temperature is 21.3 degrees Celsius. Okay, so we end up with 294 Kelvin. Okay, so just as we've done before, go ahead and plug all 5 variables into the equation. Okay, of course, leaving the one that we don't know. And then we'll talk about the algebra for how to isolate that one variable. Okay, so if we plug everything in, we get P1V1 over, and here the moles of gas is staying the same, right? The question says the same gas sample, okay, over T1, which is 283 Kelvin. Set that equal to P2, V2, which we don't know, over 294 Kelvin. Okay. So if you think about what we've done before, right, we've always cross-multiplied and divide, and that would isolate this numerator right here. Okay, think about it. If you cross-multiplied and divided, and isolated this numerator, you would also need to divide out the 0.0450, right, to isolate our unknown variable. Okay, so when you do all of that, our algebra should look like final volume is equivalent to 294 Kelvin, 0.0555 ATM, 4.28 liters. Okay, that's just that cross multiply step. Divide by 283 Kelvin. Okay, and you would also be dividing by 0.0450 atmospheres. Also, guys, look at the units going on here, right? You should know that if you have Kelvin times atmospheres times liters divided by kelvins, you still need to divide out atmospheres, right? So that liters is the only thing left standing because you know you want liters as your unit for volume. Okay, if the algebra ever confuses you, think about what you want to happen with the units, right? We want liters all by itself. So we have to have Kelvin ATM on the top, Kelvin ATM on the bottom. Okay, so when you set up this equation, plug it into your calculator, crunch those numbers, we should be getting 5.48 liters as our final volume. Okay, and think about this, right? Our volume, it increased. Does this make sense? Well, okay, our pressure decreased. You know from Boyle's laws, pressure decreases, volume should increase. That makes sense, right? We also see that our temperature increased. Okay, volume and temperature, that's Charles's law. We know that as temperature increases, so should volume. Okay, so this is a great logical answer. I'm happy with it. The next question is on slide number 21. The problem on slide number 21 reads, a 3.50 liter gas sample at 20 degrees Celsius and a pressure of 650 torr is allowed to expand to a volume of 8 liters at a standard pressure, which is 1 atmosphere. What is the final temperature of the gas in degrees Celsius? Okay, make a little note to yourself. This one's kind of sneaky. You need to convert to Celsius at the end, okay? So recall our combined gas law. Notice I'm not including moles of gas here, okay, because it's the same gas sample before and after, same denominator on both sides, okay. If we pull apart the info given to us, our initial volume is 3.5 liters. Our initial temperature, 20 degrees Celsius. You know that you need to add 273 to convert to Kelvin. So we get 293 Kelvin. Our initial pressure, 650 torr. You know you need to convert to atmospheres. 1 atmosphere is 760 torr. Okay, so our initial pressure, 0.855 atmospheres. Okay, and as conditions change in this problem, we get our second volume. Okay, our volume is more than doubling. It's going from 3.5 liters to 8.00 liters. Okay, usually we would associate an increase in volume with a decrease in pressure, right? Because we know from Boyle's law that pressure and volume are normally inversely related. Okay, remember that is assuming temperature stays constant. Okay, but in this problem, temperature is not remaining constant. Okay, so we can't quite assume that our pressure is going to decrease. In fact, the problem tells us, right, that our pressure increases to standard pressure, which is 1 ATM. So we've got volume and pressure both increasing. Okay, in order to get that to happen, our temperature is going to have to increase as well, and it's going to have to increase pretty dramatically. So that's what we are going to solve for, right? We don't know that final temperature. I apologize if my computer is running kind of loud. It's trying to process all these videos that I'm making, so please just bear with me if there's some weird background noise here going on. Okay, but just like we've been doing, plug all your variables into your equation. Okay, P1, V1. over T1 equals P2V2 over T2, which is our unknown. Okay, again, we can cross multiply and divide. T2 would be equal to 1 ATM times 8 liters times 293 Kelvin divided by 0.855 ATM divided by 3.5 liters. Okay, notice what's going on with units. We're left with Kelvin, which is perfect. That's what we want. Okay, when you plug this in, we should be getting 783 Kelvin. Okay, that's pretty hot. But remember, we said in order to get both volume and pressure to increase this way, you would really need to be heating up that gas quite a bit. Okay, but recall the question doesn't want Kelvin for our final units. It wants the temperature in degrees Celsius. No biggie. You know that you need to take away 273 to convert. You should end up with 510 degrees Celsius as our final answer. Okay, so those gas laws are kind of it for when conditions are changing. Okay, in our next video, we're going to look at, is there a way to find info about pressure, temperature, volume, or amount of gas just for one gas sample if you're not changing anything? Are these variables related in a way where you can find info about a gas sample without any changes happening? So we'll take a look at the ideal gas law coming up next. Stay tuned.